For section 13.3, we're going to be looking at finding the area in between curves. So here we have x plus 2 and x squared, and first thing we want to do is find the points of intersection. So just by looking at this, I know I'm going to have a point of intersection here, and it looks like I'm going to have an intersection at -1 and another intersection at 2, but sometimes these aren't obvious to see from the graph. So let's look at doing this using arithmetic and algebra. So first off, where these two are going to intersect is going to be where they're equal. So we're going to have x squared equals x plus 2. Now what we want to do is solve for x. We're going to move everything over to one side. Now, when we factor this, that's going to be x minus 2 times x plus 1 equals 0. So my x values have to equal 2 and -1. Great, so I know that that's going to be the interval I'm looking at for my integral. Now when you're doing these on your homework, it's not just going to ask for the x values, it's going to actually ask for the points of intersection. So what you're going to do is you're going to take these values and plug them into one of your functions. It doesn't matter because remember your functions are equal, so you're going to get the same answer either way. So one point is going to be the point 2 comma. Now if I plug 2 into this one, I'm going to have 2 plus 2, so that'll give me 4. And for the other one, if I plug -1 in, I'm going to have the point -1, 1, which matches up with my drawing I have up here. Now I want to write down the definite integral that describes the area between these curves. So my integral is going to go between the x values of -1 to 2. And remember, you're always going to do the top minus the bottom. So our top function is x plus 2 minus our bottom function, which is x squared. I always like to put parentheses just so I make sure I don't goof up if I have to distribute this guy. So remember, whenever you're doing this, it's going to be the top function minus the bottom function. The reason for that is if we look at this picture, what the integrals are doing is that it's finding all the area, okay, between the x-axis and this top function, and then we're subtracting all the area between this bottom function and the x-axis. So when we do that, we're just left with this area that we actually wanted to find, which would be this guy. So remember, it's always top minus the bottom. All right, now what we want to do is we want to evaluate that integral and round our answer to 2 decimal places. So when we evaluate this integral, what we are going to get is the integral from -1 to 2 of x plus 2 minus x squared dx. Okay, which is going to be x squared over 2 plus 2x minus x to the third over 3, and we're evaluating that from -1 to 2, which if you evaluate that, you should get 9 over 2, which is going to be, let's see, 4.5. Perfect. Alright, now the next one asks us to find the area enclosed by these two equations below. Now, here's the issue with this, is if you just look at the graph, like this graph right here, okay, the reason that this doesn't really do me any good is because if I just look at it, it doesn't actually look like there's any enclosed space. However, what I did is that I solved this algebraically, and I saw that I actually do have a little teeny tiny enclosed space right here. Okay, ever so small. And when I zoom in and I notice this, what I would like to note is that 20 over x is on top, and that -x minus 9 is on the bottom. Also, where these guys intersect, which we'll see in just a second, which is how to find them algebraically, is that I set them equal to each other, and they are going to intersect between -5 and -4. So let me show you how we do that algebraically. So the points of intersection what we're going to do is that we're going to set these two equal. All right, now this might seem like a scary equation to solve because we have an x in the denominator. But what I'm going to do is I'm just going to multiply both sides by x. So when I do that, these x's cancel, and what I get is I'm left with 20 equals negative x squared minus 9x. I'm going to move everything over to one side, so I'm going to get x squared plus 9x plus 20 equals 0. That's going to factor into x plus 5 times x plus 4 equals 0. So I'm going to have points of intersection at -5 and -4, just like I thought. Now when I set up my integral, I'm going to have it go from -5 to -4. Remember, the smaller number goes on the bottom, so since these are negative, -5 is smaller than -4. And again, I'm going to have my top function minus my bottom function. Now you can see why these parentheses are so important, because that negative is going to make this a positive x and a positive 9. So when I take the antiderivative of this guy, what that's going to give me is 20 times the natural log of the absolute value of x plus x squared over 2 plus 9x, and I need to evaluate that from -5 and -4. And when I do that, I'm going to get negative 0.0371. Awesome. So the very last question asks us not to find the area, but to find the average value. So remember, the average value formula is 1 divided by b minus a times the integral from a to b of your function f of x dx. So in this case, the average value function is going to be 1 over 9 minus 0 times the integral from 0 to 9 of 81 minus x squared dx. So that's going to give us 1/9 times, so the antiderivative of this would be 81x minus x cubed over 3, and we need to evaluate that from 0 to 9. Okay, which would give us 1/9 times 81 times 9 minus 9/3 over 3 minus, now notice if I plug 0 in this, I'm going to have 81 times 0 minus 0 over 3. That's just going to give me a big fat 0. And our answer will be 54. Okay, great. So that wraps it up for 13.3. The next section is going to be 13.4, the final section that we're going to be covering.